So now let's look at different kinds of launches, not so much considering the atmosphere, but what happens when you are taking off in a gravity field. And we have here 4 examples.
Good. 20 feet. 100 feet, 3.5 down.
In the upper left, we saw the lunar module take off from the surface of the moon. No atmosphere, but a gravity field. On the upper right, we had a sounding rocket, which took off very fast. In the lower left, we had the shuttle, and in the lower right, we had Apollo. Let's look at those again and take a look in particularly at the speed with which they leave the launch pad. In the upper right, the sounding rocket is the fastest, the lunar module, and then the shuttle, and then the slowest of all is the Saturn V rocket. So let's briefly go back, and here we go. See, that sounding rocket went right up. There's the lunar module already well up in the sky. The shuttle has cleared the launch tower, and the Saturn V is still only about halfway up the launch tower. Why this tremendous difference in the rate at which rockets take off? Well, we talked a lot when we were discussing rockets in free space about the importance of the exhaust velocity, the specific impulse being the technical name. But the faster you can push material out the back of the rocket, the more change in velocity you get for the expenditure of a given amount of propellant. That's great when you're in free space. But when you're taking off from the surface of a body which has gravity, like the Earth or the Moon or Mars, you have to worry about the weight of your vehicle. Let's imagine that we have a rocket that weighs 1 million pounds sitting on the launch pad. If your engines produce 999,999 pounds of thrust, you can fire those engines all day until your propellant is exhausted. You're not going anywhere because the thrust is less than the weight. The critical thing to consider when you are taking off in a gravity field is not just the exhaust velocity, which tells you the efficiency with which you're burning your fuel, but also the thrust to weight ratio. So what you really are interested in is the excess thrust. In other words, how much more thrust do you have than the weight of the vehicle? If the thrust to weight is greater than 1, then you're going to take off. If the thrust to weight is less than 1, as I said, you can burn your engines all day. You're not going anywhere. So let's actually look at the numbers just to understand again why the shuttle seems to take off so much faster than a Saturn V. Let's look at it one more time. The lower left is the shuttle, the lower right is the Saturn V. There's the shuttle. It's now cleared the launch pad, and look, the Saturn V was only halfway up the launch tower. So let's look at the space shuttle. So we have a gross weight on liftoff of 4.5 million pounds. The main liquid engines of the shuttle, there's 3 of them, and each one produces about 375,000. So that's a total of about 1.1 million pounds of thrust. Not enough to get you off the ground. That's why we need the 2 big solid boosters. And each of those solid boosters has a thrust of about 2.9 million pounds. So together, that's about 5.8 million. You add that up to the main engines burning the liquid fuel, and your total thrust at liftoff is about 6.9 million pounds of thrust. What's the free thrust? That is, the excess of thrust over weight is the actual thrust minus the weight, which, as we can see here, is 2.4 million pounds. So that's 2.4 million pounds of free thrust trying to move 4.5 million pounds off the launch pad. And so in order to calculate the acceleration, we divide the excess thrust, not the total thrust, remember, but the excess thrust by the weight, and that's what we have here, 2.4 million pounds divided by 4.5 million. It gives us an acceleration off the launch pad of about 1/2 g. So you're taking off at about 4.9 meters per second squared and accelerating, going straight up. Now let's look at the Saturn V. A bigger rocket, its gross weight at liftoff was 6.4 million pounds, and each of the F1 engines burning kerosene and liquid oxygen had a thrust of 1.5 million pounds. So all 5 of them together, 7.5 million pounds, which means that the thrust excess, that is the thrust minus the weight, was about 1.1 million pounds, and that had to lift up 6.4 million pounds of Saturn V rocket. So the actual acceleration, which we see here, the excess thrust divided by the weight, gives us an acceleration of a little under 1/5 g. So the shuttle had an acceleration of about 1/2 g, Saturn V slightly less than 1/5 g, 0.17 g. And that's why the shuttle went up so much faster than the Saturn V. So we've looked at 2 things here. We've looked at flying through the atmosphere and the concept of dynamic pressure, and then flying out of a gravity field, we looked at the importance of having a very large thrust at liftoff. The critical thing when you're taking off in a gravity field, the excess thrust. It's not the absolute thrust, it's the excess of thrust over the weight. So up to now, we've been looking at chemical rockets, where you take a fuel and oxidizer, you combine them in the combustion chamber to produce hot gas, which goes out the back and produces forward thrust. We've looked at solids, hybrids, liquids, but all of them basically carry their energy in the chemical energy of the fuel and the oxidizer. But there are other types of rocket engines which have different performance characteristics. And in the next segment, we'll take a little look at other types of rockets.